7.3 multivariate linear systems and row operations. We're going to start off by using elimination to solve systems of 3 variables. So on this first example, we have an equation with 3 variables, an equation with 2 variables, and an equation with 3 variables. So our goal here is going to be to make it to where we have 2 equations that have only 2 variables, the same 2 variables in it. And so right now we have one equation that has 2 variables. It has an x and a z. So what we're going to do is we're going to look at the first and the last equation here, and we're going to say, well, what could I do with these 2 equations so that I could make it have the same letters as this middle one? Well, that means that I would eliminate the y's. Conveniently, that's the one we should probably pick anyway, because the y's would eliminate really easily here. So I'm going to write out those 2 equations over here to the side. And I'm going to add them together, which is going to eliminate the y's. So I finish adding together and get 10x plus 1z equals 14. So now I have 2 equations that have x's and z's. So I can put those 2 equations together and say, okay, let's eliminate either x or z. Well, in this situation, the better variable to eliminate would be z, because it's already set up to eliminate. So let's get rid of our z's. We get 7x equals 14. Divide by 7 on each side. And we get x equals 2. So we need to know what x, y, and z are, and we know that x equals 2. So what we do is we take this answer and we plug it into any equation that we've had that has only 2 variables in it. So I could do the negative 3x minus z equals 0, but I put a 2 where x is. And that gives me negative 6 minus z equals 0. I can add z over to the right side, and I get z equals negative 6. Okay, so now I know 2 letters. I would need to know what y is. So to do that, I have to go all the way back to one of my first 2 equations, or any equation that has 3 variables, and I have to plug in both of these numbers into it. So I'm just going to pick the first one. Neither of them look like they'd be easier to deal with. So 6 times 2 minus 5y minus a negative 6. Well, that's a plus 6 if I'm minusing a negative 6. So I need to do 6 times 2, which is 12, plus 6 is 18. Then subtract 18. So negative 5y equals negative 20, divide by negative 5. And I get y equals a 4. And so then the way we write our answer is as a 3-dimensional point, x, y, z, so 2, 4, negative 6. And that's where systems with 3 variables come in, is that we can actually graph these in 3-dimensional space, which is kind of hard to do on a 2-dimensional paper. But you could graph these, and it's talking about if I have 3 lines in a 3-dimensional space, where is their point of intersection? So let's do another one, and this time we don't have an equation that only has 2 variables. So what we want to do is we want to pick either x, y, or z to eliminate twice. So looking at this, really all of these various variables are pretty easy to eliminate. We could pick the x's, and we would just have to change 2 of the equations to have negatives. We could pick the y's, and we'd have to multiply at least one equation by negative 2. We pick the z's, multiply by 2 and by 3. But let's just go with the x's. So I'm going to take the first equation as it is, and then I'm going to multiply the second equation by a negative 1, so that my x's will eliminate. Negative x minus y minus 3z equals negative 14. Now I'm going to eliminate. So what actually happens here, if I look, is I was only trying to eliminate my x's, but I also eliminated my y's, which is a good thing, I guess. I guess it makes it a little bit of an easier problem if that happens. Z equals 3. We got to that point sooner than we would have if we had had another y here. Now let's do the first equation with the last equation. So we're going to have to multiply the last equation by a -1. So x plus y plus 2z equals 11 minus x minus 2y plus z equals -5. So we need to eliminate. And so now we have an equation with two variables. If we had ended up with something on our first one, like y minus z equals -3, then we would have to do elimination again, because we would have to get rid of either y or z. But since we actually got rid of both of these, and we got z equals 3, then I can put that 3 in and I can go ahead and start solving for my variables. So that y equals 3. And then I take z and y and plug it into one of my first three equations. So the first one looks pretty good to me. X plus 3 plus 2 times 3 equals 11. So x plus 3 plus 6 is 9. So x equals 2. So my point is 2, 3, 3. So that's the first way that we can solve systems with three variables. The next thing we want to look at is using matrices and row operations to figure out how to, or to solve a system. And so this actually really comes in handy if we're doing more than three, because elimination is not really that bad if you have three variables. I mean, obviously it's not like probably what you want to spend all of your time doing, but it works out pretty nicely most of the time. But just think if you had 4 or more variables, that could get really, really tedious really fast. So we have these row operations that we can use. The first thing we want to talk about is what an augmented matrix and a coefficient matrix are. And so let's actually start with the coefficient matrix. And I have this system here. From example 2, we're going to write the coefficient matrix for that. Well, coefficients are the numbers in front of our variables. So the coefficient matrix simply has the numbers in front of our variables. Since we have 3 variables and we have 3 equations, that's going to make it a square matrix, a 3 by 3. Okay, so that's our coefficient matrix that we'll be using in a little bit. Okay, the augmented matrix takes all of the numbers we have. So we don't just have the coefficients 1, 1, 2, but then we also put what that equals. And I personally like to draw a line right here, and a lot of teachers do, but your book doesn't, to show that that's where the equal sign is. So then I would do 1, 1, 3, and then that equals 14, 1, 2, -1, 5. Okay, so that's just how you would write a coefficient matrix or an augmented matrix. The augmented is because when you augment something, you like add something to it. So we took the coefficient matrix and we added a column here at the end for the right-hand sides. Now we're going to talk about 2 forms that we can get our matrix into. One is called row echelon form, and there's like specific things over here 1 through 3 about what it means to be in row echelon form. But basically your goal, if it tells you to get it in row echelon form, is you want this diagonal right here to be 1, 1's across like this diagonal, and underneath the diagonal over here we want zeros. Okay, so the first element in each row that is besides 0 is 1. We have 1, 1, and 1. And in front of the ones we have zeros. Reduced row echelon form takes it a step farther, and we still have the diagonal of 1. We have these zeros here, but we also have zeros above the diagonal. So that's reduced row echelon form. So depending on what question they ask us, these are our 2 options that we're trying to get to. And the way we can do that is we're going to take our augmented matrix for our system and we're going to perform row operations on them. and there are 3 row operations, which is down here at the bottom, that we're allowed to do to a matrix. The first thing we're allowed to do is interchange any 2 rows. So if you start off, and we actually label, like we actually are going to end up talking about this as row 1, row 2, and row 3. So something that we're allowed to do, for example, is interchange 2 rows. So I can switch row 1 and row 2 around so that this row is actually the one on top and that the top one is actually the one in the middle. And I can do that with any of my rows. I can just make them switch places. But all of the numbers have to stay in the same order that they, like column wise, left to right, as they were before. The second thing I can do is multiply all elements of a row by a non-zero real number. So a lot of times that's going to be a situation where we're trying to get a 1. We can multiply by something to get a 1. We have to do that to the whole row. And the third one is that I can add a multiple of one row to any other row. So those are the 3 things we're going to do to to get our matrices to row echelon form or reduced row echelon form.